Hi guys, welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining me here today for our discussion of quadratic functions. If you've been following along with us in our functions unit, you will know that we've talked about the 7 different types of functions that a student is likely to encounter in an Algebra 1 or Algebra 2 class. We've talked about how domains go into our function and range values pop out of that function. And we've talked about how those functions are going to look when graphed on a coordinate plane. We've also talked about how if we list those functions in vertex form, those graphs become much easier for us to graph. But for today, I'd like us to pay special attention to the quadratic function because quadratic functions have lots of patterns in them that are useful for us to know and that will be very helpful for us when we are trying to create their graphs. So what I have done is I've listed the functions f of x equals x squared, g of x equals x squared plus 2, and h of x equals x squared minus 4, all on the same slide. What I'm going to do is I'm going to generate some values of x. I'm going to insert them into my function and see the y values or the f of x values. And then we're going to look at the graph and see if there are some patterns that pop out for us. You will hopefully remember from our vertex form of the function that these values on the end should tell us something useful. We will talk about that again in case you've forgotten it, but there's also another pattern that's hiding in here I want to make sure that you see. So don't skip ahead assuming you already know this. Now, since I'm going to be plugging lots of values into these functions and getting values out, I'm going to go ahead and point out that I'm going to do this rather quickly because most of that is going to involve computation, and the computation is really not the focus of the lesson today. I am going to recommend that you pause the video at intervals, especially if I do a computation that confuses you, and that you make sure that you understand where our output values are coming from. So even though I'm rushing through it, I'm assuming that you are pausing as necessary in order to see what is happening. So let's go ahead and dive right in. We'll start with f of x equals x squared. This is known as a root function, meaning this is the simplest form of this type of function. I cannot have a quadratic function unless I at least have an x squared. Every other quadratic function is a variation on this basic idea. And I'm going to create some x's, plug them in, and see what comes out. Let's say I were to insert a 0 into this function. 0 squared equals 0, so I would represent that as a coordinate on my coordinate plane. If I plug a 1 into this function, 1 squared is 1, which is also a point on my coordinate plane. If I plug a 2 in, 2 squared is 4, which is a point on my coordinate plane. 3 squared is 9, which is also a coordinate on my coordinate plane. You can begin to see the parabola starting to form. Let's go ahead, since this is going to go off my graph before I reach the 4, let's go ahead and stick in a -1 and see what happens. -1 times itself is a 1, which gives me this point. Now this point right here is very important and very helpful for us. Do you know why? Well, hopefully you realize that it's because it is on the other side of the parabola. It is reflected across the line of symmetry from this 1 Once I know that this is on the other side, I know that this is the vertex. It's the minimum value of this parabola. And I can begin to use that line of symmetry to reflect and find the other sides. I've got my -2, 4, and I've got my -3, 9. You get that nice, neat parabola. Let's take a look at the second one. X squared plus 2. If I were to stick in a 0, 0 squared is a 0 plus 2 gives me my 2. There's my coordinate. If I plug in a 1, 1 squared plus 2 is 3. If I plug in a 2, 2 squared plus 2 is 6. And I'm going to do this just a little more quickly this time. Notice I'm off my graph now, so I'm going to come back the other direction. If I plug in a -1, -1 squared is 1, plus 2 is 3. And there you see I've got the other side. Once I have the other side, I can use my line of symmetry to reflect and get the other side as well. And there's your graph. Notice I did fill in the values in the table for you, but that was not necessary because I could have used the line of symmetry. For the sake of time, I'm going to speed through this last one. if you're in my class, I'm going to recommend that you pause the video and you try and get these values on your own. But this is what your graph is going to look like. Notice, once again, it looks the same. Let's talk about tips and tricks. If I add a number after my x squared, can you tell what's happening to my parabola? Well, hopefully you realize, number one, this number right here tells you what your y-intercept is. Notice I'm crossing at 2. Notice here I'm crossing at -4. Notice here I'm crossing at +0. As long as all you have is a plus or minus value at the end, it's always going to tell you where the y-intercept is. Second, that y-intercept, as long as it's just the x squared plus that value, or plus the 0, is also going to tell you where your vertex is. My vertex is at -4. My vertex is at +2. My vertex is at +0. And it also tells you where your line of symmetry would be. Line of symmetry is on the y-axis. Line of symmetry is on the y-axis. Line of symmetry is on the y-axis. As long as it's always x squared with something either added or subtracted, your parabola will always be centered around the y-axis. It will move up or it will move down based on this value. For those of you that were with us for our vertex form of functions, this would be a k value because k controls up and down. If you're not familiar with that, check out the vertex form of functions video. There is another pattern I do want to make sure that we see while we are here, and that is quadratics will grow using a 1, 3, 5 pattern, or they will grow by increasing odd numbers. Take a look over here. I'll show you what I mean. See how this was at 0? This point is up 1 from 0. But when I go from this point to this point, that's an increase of 3. And when I go from this point to this point, that's an increase of 5. If I can spot that 1, 3, 5 pattern, once I know the vertex, all I've got to do is go over 1 up 1, over 1 up 3, over 1 up 5. Any idea where the next point would be? Well, it's over 1 up 7. And take a look, that happens over here as well. Up 1, up 3, up 5. Over 1 up 1, over 1 up 3, over 1 up 5. The next one would be over 1 up 7. Same thing happens here. This is an increase of 1, an increase of 3, an increase of 5, followed by an increase of 7. The next one would be an increase of 9. As long as all I've done to my x squared is subtract 4 or add 2 or add 0, it's always going to grow with that 1, 3, 5 pattern. Now let's take a look and see what happens if instead of adding something to the end, I change the number in front of the x squared. I'm going to do these a little faster this time because, again, our goal is not to spend time calculating. At this point in our functions unit, we should be pretty good. We should be pretty good at sticking values into the function and graphing the coordinates. Instead, what I want us to focus on is when I put those values into my table and when I graph those coordinates, what kind of patterns do I see? Because remember, ordinarily we grow 1, 3, 5. In fact, the number in front of the x squared still uses that 1, 3, 5 pattern, but notice it multiplies that rate of growth. See where I had a 1 here? Now I have a +2. Do you see where I had that 3 before? I now grow by a +6. And my next point is going to be a +10. This acts as a multiplier on how fast your graph grows. So if I have a 3 in front, instead of growing 1, 3, 5, I'm going to triple that. I'm going to go 3. 3 times 3 means 9. 3 times 5 makes 15. Changing the number in front multiplies that rate of growth, or that 1, 3, 5 pattern, by whatever that number is. If you were with us for our vertex form of a function lessons, you will remember that this value could be described as the A value in the vertex form. It's changing the steepness of my graph. So why have I spent so much time doing this? Well, if I know all these things that we just talked about, and I start with a knowledge of my root function, I know it's ordinarily going to start at 0, 0, and I know it's going to grow using a 1, 3, 5 pattern. If I give you a function like this, 2x squared minus 5, I know this minus 5 is going to move that vertex down 5 spaces. And when I look and see what's in front of my x squared, that tells me that instead of growing 1, 3, 5, I'm going to double that. I'm going to grow 2, 6, 10. So I'm going to come over here, I'm going to go over 1 up 2. Then I'm going to go over 1 up 6. Then I'm going to go over 1 up 10. And since I know this is my line of symmetry, I get the other side of that graph without having to plot anything. Notice, we just graphed a quadratic function without putting any values in our table. That's the value. You might want to pause the video and try this last one on your own. I'm going to do it exactly like I did these other two. I'm going to look here and say, I know what the root function looks like, but this time the whole thing is going to move up 7 places. So I'm going to start up here at 7. And I also know that the number in front is going to triple that 1, 3, 5 pattern. So instead of growing 1, 3, 5, I'm going to grow 3, 9, 15. And because it's negative, I also know the whole thing is going to go upside down. So I'm going to go over 1, down 3, over 1, down 3, down 9, down 15. Then I'm going to get the reflections across that line of symmetry, and we have our graph. Notice, this moves the whole thing up and down. This value triples the rate of growth, and the negative sign says instead of growing, I'm now going down. Not bad, right? This is going to save you a lot of time as you're trying to graph these quadratic functions. One more thing I got to show you. This is really cool as well. This is a quadratic function written in standard form. Notice I have 2x squared minus 8x plus 4. The standard form of an equation has the x squareds first, then the x to the first power, and then the x to the 0. Remember, anything to the 0 power is a 1, and 4 times 1 is just 4, so we don't write it down. We describe it over here as ax squared plus bx plus c. What we know is that this plus 4 is going to move the entire graph up 4 places. We also know it's going to grow twice as quickly as normal. So instead of growing 1, 3, 5, it's going to grow 2, 6, 10. What we don't know is what this minus 8x in the middle is going to do. That's why we have to be extra careful when working with quadratic equations or quadratic functions if they have this middle term right here. Be very, very careful. All the examples you've worked with before now have been just adding a 4 or adding something to the end, or doubling or tripling x. If you were in my class and you did the vertex form of functions, you also did some functions that were, or some quadratic functions that were in vertex form. This is not in vertex form, so we can't rely on our a, h, and k. Instead, what we've got to do is we've got to memorize one more pattern. And that's this. If I have ax squared plus bx plus c, and I'm talking about this specific example right here, 2x squared, notice I make this minus into plus negative, so it fits the pattern. And then I have a plus negative 8x, and then I have a plus 4 at the end. Notice that the A position is occupied by the number 2, the B position is occupied by a negative 8, and the C position is occupied by a 4. In order for me to graph this quickly and easily, I'm going to remind you or recommend that you find the line of symmetry first. Now, up until now, that line of symmetry has been very easy to find. On the examples on the previous slide, it was always here on the y-axis. In our lesson on vertex form, we could use h and k to find that. But if we have an equation in standard form, or I should say a quadratic equation in standard form, the line of symmetry is going to be in a different spot. You need to know the pattern for finding that spot. And we would say that line of symmetry or axis of symmetry is always going to be located at the line x equals negative b over 2a. If you're in my class, you need to memorize this, because if you know this pattern, all you have to do is plug in the b from your specific equation and the a from your specific equation, and you can find that line of symmetry. In our case, x equals negative, b is negative 8, so negative negative 8 over 2 times whatever a is. A happens to be a 2. I need to make this purple instead of blue. That's slightly confusing, isn't it? Either way, when I simplify this, negative negative 8 becomes 8 over 4, so your line of symmetry is going to be at x equals 2. That's right here. Once I know where my line of symmetry is, I'm going to find my vertex next. And the way I find that vertex is I use this value for my x. And I plug it in here. There's my 2. If 2 goes into this function as an x, notice I color-coded it to match this original pattern. All I have to do is perform some computation here to find out where the y value of my vertex is. My vertex is the point 2, negative 4, which is here on my graph. Now, I did this computation very quickly. I skipped over most of it. You're going to want to make sure that you're comfortable with this computation and ensuring that you're getting the value of negative 4. Because once I know the vertex, I can go back and take this doubling of my 1, 3, 5 pattern to finish this. So instead of going up 1, 3, 5, I'm going to go up 2 and get the reflection. I'm going to go up 6 and get the reflection. I'm going to go up 10 and get the reflection, and there's my graph. Now notice I did show the computation over here, but it was not necessary because of my 1, 3, 5 pattern, or in this case my 2, 6, 10 pattern. Let's go ahead and try another one. G of x equals negative x squared plus 2x plus 3. Notice this is in standard form again. I have my x squared first, my 2x second, and my 3x to the 0, because there are no x's, third. If I take standard form of a quadratic equation or function, and I copy down my pattern here, notice it's g of x this time. Notice that I have a negative 1 in front of x squared, I have a 2 in front of x, and I have a 3 out here by itself. That means my a is a negative 1, my b is a 2, and my c is a 3. Can you use the pattern that we talked about a few minutes ago to find that axis of symmetry or line of symmetry? I'm going to recommend you pause the video and do that on your own. I'm going to go ahead and plug in my 2. I'm going to go ahead and plug in my negative 1. And I'm going to get that my line of symmetry is at x equals 1. Once I know where that line of symmetry is, I'm going to take that 1 and I'm going to plug it into this pattern right here. I'm going to recommend you pause the video, try that computation on your own, but I'm going to go ahead and tell you that I get a positive 4. There's my point right there, 1, 4. At this point, I would look up here and see that this has a negative 1 for A. That means that I'm going to grow by that 1, 3, 5 pattern, but it's going to grow upside down this time. So if I go down 1, I get the reflection. I go down 3, I get the reflection. I go down 5, I get the reflection. I go down 7 for the next one, and there is your graph. Notice, by the way, if I were to plug a 3 into this, I would come up with a 0. That's just a nice, neat little way for me to double check and make sure that I haven't made any small, careless errors. Not bad, right? Here's one more. Again, I'm going to recommend that you try this one on your own before watching me do it. I'm going to do this one just a little bit faster because you should be getting good at it. When I look at this, my A is a -3, my B is a -18, my C is a -24. Knowing that, I can take this pattern that I'm memorizing and get -18 over 2 times -3, and I get my axis or line of symmetry at x equals -3. Once you know where your line of symmetry is, you take that value, you plug it into your table. I'm going to skip through the computation, recommending that you pause the video and try that computation on your own. I come up with a +3. Once I have that point, I'm going to look over here and see my pattern says I'm going down 3 times my 1, 3, 5 pattern. So instead of going down 1, I'm going to go down triple that. Instead of going down 3, I'm going to triple that and go down 9. And then I'm going to go ahead and get the reflections. And there we go. Not bad, right? If you wanted to plug a value in like 0 and find your y-intercept, certainly we can see that we would cross the y-axis at 0, -24. We are going to try one more because it does have something in it that's a little bit tricky. I'm going to recommend that you try this on your own. Pause the video if you get stuck and listen to me explain it. I'm going to go through this one just a little bit faster. Again, I look at my pattern. A is a 1/2, B is a 5, C is an 8. I plug those into my formula. I get -5 over 2 times a half, which gives me a line of symmetry at -5. So I draw that in, and then I take my -5 and put it in my table, and then I perform some computation. I come up with -4.5. Now, I'm not a big fan of this coordinate because I don't like to start off on a fraction or a decimal. It makes it much, much harder to count. It's also going to be difficult because my 1, 3, 5 pattern gets cut in half. Meaning, instead of growing 1, 3, 5, I'm now going to grow a 1/2, 1.5, and 2.5. It's going to be a little tricky. Be extra careful here. I'm going to go up a 1/2 when I go over 1, and then I get the reflection. I'm going to go from that spot up 1.5. That's up 1.5 over again. Get the reflection. I then go up 2.5. There's a 1/2, 1.5, 2.5 puts me right about there. I get the reflection. After the 5 halves, of course, I'm going to have 7 halves, which is up 1, 2, 3.5. And the reflection. I'm then going to get 9 halves, which is up 4.5. That's a 1/2, 1.5, 2.5, 3.5, 4.5 over 1. And then the next one's going to be off my graph. So there's my picture. Just be extra careful if you end up with decimal values like this. Hopefully this has been extremely helpful for you. Hopefully you've seen some patterns that are of use. Again, it's going to be extremely important that you make sure you memorize both what the standard form of a quadratic function looks like, as well as how to find that axis of symmetry. You memorize those 2 formulas, the rest of this is pretty straightforward. As always, I do appreciate you joining me. Thank you so much for taking the time to be with us. Make sure you hit that like button so that I can see your big old thumbs up and know that somebody's out there watching and enjoying this. Make sure you ring that bell to turn on your notifications so you can hear all the new and exciting things coming from us here at Nunley Math. As always, I wish you the very best. Take care of yourselves. Bye-bye.